Hello, and thank you for your interest in our work. We are at present investigating the possibilities of a consumer drone to improve pasture management in the future. And we are Beat Reidi, Michael Sutter, and myself, Philipp Aebischer, working at the School of Agricultural, Forest and Food Sciences in Zollikofen, Switzerland. As a decision-making aid in pasture management, dry matter yields are for now estimated using a rising plate meter. But unfortunately, only punctual measurements are possible with this measuring device. This leads to an estimation error of about 250 kilograms dry mass per hectare. With help of a DJI P4 multispectral, we are able to fly over large areas of pastures. After stitching and marking the regions of interest of the 3 different sites, we do the calculations with an in-house Python solution. What does it look like in detail? We are at present still using the grid method to scan the areas. This guarantees a better representation of the depth. The frontal and side overlap was chosen to be 70%. We are flying with the support of a mobile, real-time kinematic station, although in the past we had to realize that the position must still be adjusted afterwards, or alternatively must be flown with ground control points. Our training data was collected at 3 different locations. At 2 locations we flew at 35 meters and at the last one 50 meters above ground. It should also be mentioned that the areas in Zollikofen and Langenthal are grass growth trials and the one in Schüpfen is a pasture trial. This is a great advantage because it allows us to generate a heterogeneous set of data for later modeling. In a second step, the stitching is done with the standalone software Agisoft Metashape Professional. We correct the reflectance over the whole flight with a reflectance panel from MicaSense and as well the light conditions during the flight. The integrated light sensor of the DJI P4M takes care of the corrections during the flight. A 3D model with a pixel size of 4 cm and an orthomosaic of the 5 channels red, green, blue, near infrared and red edge with a pixel size of 3 cm are exported. The shapefiles are defined in the open source software QGIS. To artificially generate a higher number of training data, we have divided the individual trials into 3 parts. Using an in-house Python script, the X and Y offset corrections are then made to ensure that measurements are always taken in the same test field. The vegetation indices are also calculated within a Python script. 16 in a first step because we do not know the influence on the model yet. The last step is the most important. Here we calculate our digital terrain model from a combination of rank filters and 2D convolutional operators. This has great advantages because georeferencing is no longer necessary. Let's call it a digital mowing machine. This digital mowing machine works as follows. In a first step, missing data is interpolated. This is especially of advantage at the edges, so that after smoothing, some of the original digital elevation model is left over. In a second step, a minimum filter of 0.5 meters by 0.5 meters is used to find the minimum in the area of that kernel. The same in a second pass with a slightly larger filter, 0.7 by 0.7 meters. The whole thing is now smoothed out. This is done with a 2-dimensional convolutional operator, a Gaussian filter. Almost done. We now have our digital terrain model calculated from the digital surface model. The difference between the two gives us the hair of grass per pixel. And the average height is what we use for further calculations. One last step is missing. With larger inclinations, the ground sample distance no longer matches at all positions. This is counteracted by smoothing the calculated height again. And this is what it looks like in a crosscut of a field. In blue, we see our surface of the 3D model, just as it is calculated by Agisoft. In orange, the smoothing we calculated. We can now evaluate this and compare it with the measured height. The measured height is shown on the y-axis. The x-axis presents the measured height of the digitally mowed fields. For the data on the y-axis, the fields were each cut on the same day and flown over again. The difference of the two overflights gives the measured heights. The graph shows 3 locations. In blue and cyan, 2 grass growth experiments. In yellow, a grazing experiment flown last year. An R² of 0.9 shows us that with our digital mowing machine, we are close to the measured values. A few words about the error calculation. The error was calculated empirically. This means that the difference between 2 overflights on the same day was calculated. In a perfect world, this would be 0. The positive deviation of 1 centimeter in the left histogram is due to the fact that before the second overflight, neighboring fields were cut. And since the cuts partly reach into these fields, it slightly distorts the error calculation. The same in the right histogram, with the difference that here the digital terrain model was calculated for both overflights. This also explains the asymmetry. In summary, our error is probably overestimated and should be even smaller. This is still work in progress and will be adapted as soon as possible. But for now, this is showing us that we're on a good way. We can now use this 3D data as features for our model. So let's have a look at our model parameters. Originally, we worked with 32 parameters and the dry mass as label, ground truth. At the moment, we are working with 14 features. The average height, its standard deviation, the minimum height and maximum height from our 3D model. The NDVI, Normalized Difference Vegetation Index, SAVI, Soil Adjusted Vegetation Index, and the excess red index as most important indices. And the 2 features, month and shutter speed, these help us to have a robust model during different times of the day and seasons. This leads us to the following results. At the moment, our model performs with an R² of 0.84 and an error of 267 kilograms dry mass per hectare. This looks pretty good. The error calculated on the average total yield is 13%. The mean error also shows us that our model only slightly overestimates the true value during training, currently around 49 kilogram per hectare. But how good is the forecast on fields never seen before? We can see that here. It must be mentioned that the measurements taken in July were right on the field next door, at practically the same location. The dry matter yield was measured by Agroscope. They have kindly provided us with the data. The measurement in Bretzwil and Gampelen were taken at other sites, shown in red and magenta. The 2 overestimated outliers in Bretzwil are due to a different botanical composition. The stem-to-leaf ratio was different in these 2 cases compared to the other experimental areas. Looking at the metrics, we observed the following. The R² value has dropped by half. At first sight, not so great. But considering some missing data in the low range and the outliers that have to be categorized clearly, not that bad. The error corresponds to the expectations. At about 300 kilograms per hectare, it's somewhat larger compared to the training data. This error should also improve with more test data. The measured total yield remained in about the same range. Therefore, the bigger normalized error, 16%. The average error is comparable to the one from the training. The model slightly overestimates reality, which so far the two outliers may as well be responsible for that effect. All things considered, our model looks very promising. There are still some gaps to be filled in and further tests to be carried out. So, what are the next steps? The results show us that we have to test our model performance on more sites. Further, we will continue feeding our model to cover the 3 seasons. This is not yet completely done. The training data for September are pending. And then finally, use this model for the estimation of pasture residues. We have to define the pasture residue in a meaningful way first, so that it can be correctly segmented on the image processing side. First attempts look promising. A small preview as the conclusion of our presentation. Thanks for watching.